Basis. Thanks for sure.
Thank you. It's good to be back. Those of you that attended the first iteration of No Such Con, and feel honored to join you guys again. Last year's talk was about taint analysis for the purpose of looking at crash triage, so that you can look backwards through the execution path to see where your which bytes influence the crash, and also to look forward using symbolic execution to try to determine exploitability. So this talk builds upon that a little bit. And so if there's some areas where I mentioned taint analysis, we're going to go pretty lightly over that this talk. But there's material that I can reference you to with my previous talk, and then also a good paper from Carnegie Mellon called Everything You Wanted to Know About Taint Analysis and Were Afraid to Ask. So, and you can catch me later if you have any other questions. Just a brief introduction. As you mentioned, my name is Richard Johnson. I am the manager of the Vulnerability Development and Research Team inside of Cisco Talos. You may have known us formerly as SourceFire VRT. Last year, Cisco acquired SourceFire, so we're now in a new organization that covers developing malware products and malware research and informing basically all of the data that goes into the IPS. And part of that is us finding original vulnerabilities in third-party products and software and developing tools for triage to help out our team. So this is a culmination of some of that effort that pretty much started about 2 years ago with the fuzzing side of things, with the triage and the taint analysis side of things. And this talk was originally a two-part talk that turns out to end up really taking about an hour and a half to give properly. So today, since we only have about 45 minutes, I'm going to focus heavily on the concolic execution, the fuzzing side of things, because I think that's really where we've made the most gains. And hopefully we'll be back next year to talk a little bit more about some of the diffing stuff. If I do have time at the end, I can show you some results. And we will be releasing some free tools that are related to improving the heuristics in BinDiff, and you can read about that later on when we release it on a blog post and whatnot. But the slides will be in here as well, so if you want to reference those later, go ahead. So just first of all, can I maybe get a raise of hands if you were here last year and saw my talk, just so I get an idea of maybe some people that have context? Okay, great, excellent. That's great. The Parisian hacking scene is really strong, and I'm always impressed with the people that kind of understand the harder program analysis level topics. So as I said, we'll be extending on that, and instead of looking at crash triage that we might have found with other fuzzers or other source code analysis techniques, now we're looking at true automated test generation. So what is automated test generation? The goal is to exercise a program fully, right? You want to reach all possible conditions in the program that are available to you through the interaction of user input and the logic of the code. And some of those interactions will be unintentional, which will lead to crashes and exceptions. And those are really what we're looking for. And when you look at a program, something like IDA or a disassembler, we look at it structurally in the sense of a code graph. And the code graph being vertices that are your blocks of code, whether they be at the abstraction level of functions or basic blocks of code, and then the branching in between them would be the edges, so your jumps or your calls. And in order to get full exercising of a program, you want to be able to traverse all branches to all vertices, and based upon having one set of inputs, we want to figure out a way to go from a known set of inputs to what are the inputs that we don't know how to create, rather than having to look at specs and go find other samples that already exist online. We want to fully exercise all possibilities in the format parser that are available. So the way that automated testing happens pretty much breaks down to two approaches, right? We have fuzzing, the generic term fuzzing, which is classified in a few different ways. We can randomly mutate an input that we already have, or we can intelligently mutate an input that we already have, things that would infer some part of the structure of that program. Syntax model-based fuzzing like Codenomicon and Protos, which came out of Oulu in Finland in about 2004, they would take the RFCs that describe a protocol and the BNF grammar and encode that to model the syntax and the interaction logic, meaning like the sequence of events that you might send this data, and then they mutated that. So rather than mutating concrete data that you would see in one packet. They actually mutated the format and description of the structure because they were comparing the functional definition against the actual implementation. So that's another approach as opposed to just byte flipping and code flipping. And then we have more intelligent mutation fuzzers that try to look at series of strings and sliding windows of n-gram analysis, and that would be something we'll drill down into a little bit further in the upcoming slides. And then finally, there's direct API interrogation for fuzzing, and the problem with this, of course, is that you can send you can send random integers as part of your parameters to a function and hit boundary cases and look for integer overflows, but we always have the problem with reachability and not knowing if you can actually send the triggering integer value through the code logic that gets there. There's oftentimes constraints in the way. There may be checksums, there may be simply no possible feasible path starting from an external input to get to that API. So concolic testing is what we're really interested in, though. Concolic testing is a relatively modern approach to applying program analysis theoretical concepts to the concept of fuzzing and trying to create crashes. And the way we do this is we need to instrument a program. So we need an efficient instrumentation platform. And we need to be able to instrument it at a very high granularity down to the instruction level. And then not only that, we need to be able to track data flow. And that's what generally is referred to as taint analysis. And after we observe the data flow, then we know which parts of the code actually, which instructions in the program actually interact with your external input, right? The file or packets that you're supplying and have control over. And then finally, we want to not only see which instructions interact with the code, but we want to see what precise instructions those are, because some of those will influence the control flow that you actually exercise in the program. And if our goal is to succeed in a full reachability exercise over the program graph, then those are the instructions that we need to clue in on, and those are the ones that create the constraints that determine which parts of the program we get to. And finally, once we have one representation in this form that basically allows us to describe what a code execution path is and all the constraints, we want to be able to manipulate that symbolic formula that represents that path such that we can generate new paths and pass that off to something like a SMT solver, which will give us a new input that will reach a different path. So that's what we're going to drill down into in the coming slides. So the more advanced fuzzers that we use, because once again we're trying several approaches and we want a very practical approach, a pragmatic approach that's multi-layered. So of course we do use traditional mutational fuzzing. And Radamza is the preferred one, also from the Oulu SPG group out of Finland, same guys that made Protos and took the BNF grammar mutation. But Radamza actually is a meta-fuzzer that has about 20 or 30 algorithms in it, going all the way back to your traditional byte flipping, swapping, copying, truncating, things that you would find in any other pretty average generic fuzzer. And then also some better string identification algorithms, so things like n-gram analysis or sequitur approaches to looking for substructures that are similar across a corpus of files and realizing that there are relationships between data types automatically. So if you're not familiar with Radamza, that's an off-the-shelf open source project. You can compile it from Windows or Linux. You have to use Ming to do it, but they have like a release that's about 1.5 years old for Windows. But if you do use Windows, I highly recommend using the subversion tree. There was research last year that focused on fuzzing XML, and so then they added XML-specific mutation parsers. And so if you're doing mutation fuzzing, just a blind mutation fuzzing where you just give it a set of files and Radamza is pretty much the way to go. But of course, the problem with mutational fuzzing is that you're really only going to be able to manipulate the data that's already in the file, right? So when it comes down to constraints, there can be a particular header or magic number or field or nonce, whatever you want to call it, that has to be a specific value. And if the value isn't there, then you'll never exercise the part of the program that's designed to parse that type of structure. So if I open up a complicated document file or complicated protocol, and I never actually observe a certain data type in the original input, it's very, very, very unlikely that you're going to be able to generate the static 32-bit value that might get you into a whole other area of code. So in concolic fuzzing context, the canonical example that's in all the papers that date back to, I think the first one was 2004 or 6, use this very, very simple 4-byte comparison, just to show you that doing bit flipping to get one precise exact value, a 32-bit value, is pretty much outside the reasonable bounds of how much time you want to spend fuzzing, right? It's not going to happen most of the time. Your 1 out of 4 billion or so attempts will get you into a new part of the parsing code that you weren't in before. Or if there's a static comparison, like a simple magic number or something like that, you're just not going to get to exercise that code. So ultimately, no matter how much we refine our string identification, when I say string identification, it's strings symbolic, like sequences of bytes and things like that, not just text or ASCII strings. But no matter how good we get at identifying sequences of bytes, we're only going to be able to analyze the data that we already have available. So that's why you need to look at the code and look at the execution and the logic inside to understand which data inputs need to be modified to reach out other parts of the code. And also, like I did mention checksums, but like checksums is one of those classic examples where people would use mutation fuzzers and wrap them in a secondary layer that's specific to every little application, so that you made sure that you fixed up the checksum at the end. Otherwise, the whole effort of fuzzing is going to get tossed out. Well, you can not automatically identify things like simple checksum functions, and something like a concolic fuzzer will adhere to the restrictions that are imposed by simple checksums. So later on, I have a demo that our first demo will be showing exactly how easy it literally takes about 90 seconds to reach all paths in something like this and solve that problem. And this is a simple example, but that just scales, and it's a time to processing power to chain a bunch of those together. So basically what we're down to is looking at the academic research that started, I guess it's 2005, out of Berkeley and Stanford, University of Illinois, and basically the idea was, we've had the concept of being able to apply reasoning to logic and code through formal methods, but what we haven't really had until fairly recently was a very efficient way to do the observation of a program to begin with. So tracing programs is very slow, right? The formal theory behind being able to solve the problem of branch logic inversion and things like that, that's been around for quite some time, but it wasn't really until about 2005 when Baptiste Godefroy and Ken Kushik-Sen in the same year started modifying compilers so that they were instrumenting the program logic to allow it to output data that they could then use to pass on to SAT solvers and SMT solvers. And then later on, 2006, just a year later, Dawson Engler from Stanford created something called XE in a paper, which you might now be familiar with as Qt. And so that's a system that's actually survived to this day. And Qt ended up evolving into JQt, which had a little bit more applicability at the source level because they had the ability to maintain a little bit more context. Dart was the research that was the origin point for what became Sage, which is really what informed me and directed me down this path. And then later on, I went back and researched the rest of this. So what are the core concepts that we need to consider in concolic testing? First of all, the tracing, as I mentioned, is pretty much, ironically enough, the simplest but most difficult portion of this whole thing. The thing that hasn't been solved yet is how to make a very efficient trace so that you can do online taint tracing while you're analyzing a program. We end up doing recordings and then future passes to do the analysis and things like that. So it all starts with code coverage, because we need to understand where in the program we're going. And the rest of the analysis is very expensive. SMT solvers are very slow, taint analysis is very slow. So the first thing you want to know is when you take one of these new inputs, where are we going in the program? Just what's the reachability that we've achieved on each new input? So those that aren't familiar with code coverage, it's just simply basically hooking every jump and entry point to a basic block and recording which parts of the program you get to. You can do this a whole bunch of ways. Originally, Native Debugger API, there's a whole bunch of code coverage tools for ptrace and for debug-eng. those tend to be slow. There's actually a bug in Debug-Eng a while back where if you had something like more than 10,000 breakpoints, the adding to the list became exponentially slower. Their list management was poor. And so if you were actually trying to debug anything complicated that had to insert, hundreds of thousands of breakpoints, it just simply wasn't going to happen. It just fell over. So if you're only doing code coverage, another option is to modify the operation of the trap flag. You do this through an MSR register, and it essentially changes the trap interrupts such that it breaks, instead of on a single instruction, it breaks on the basic block entry points. Of course, code coverage isn't the only thing we need, so it doesn't really apply here. It's also really not that much faster because you're still doing a transition from your user mode context down to a hardware interrupt, which requires several layers of execution context switching, and essentially it's just a very slow way to say, hold on, I want to look at what's going on here. I want to observe what the process context is. So another option would be static binary rewriting, but there really isn't a very accessible, robust static binary rewriting platform out there. Piotr Banya, who's actually now part of our team, has written a static binary rewriting platform in the past, but I don't think it became open source. There's other academic projects at University of Maryland in the US, a few others. So there's definitely active research going on here, but unless I have missed something on the internet with my Googling, I haven't really seen a static binary rewriting platform that can be applied to commercial off-the-shelf software like Microsoft Word and large-scale targets that we're looking for. So the current solution that is pretty much really the trend these days is to use a binary instrumentation platform. And we're going to talk about that in just a second. So the one slide that I do have on Taint analysis just is a description of how it works. And basically what you're doing is you're hooking the source and sink. You're looking for the path between the source and sink of where the data goes during the execution of a program, right? So you open a file descriptor, and then later on you read from that file descriptor, and typically you will indicate which file names or network sockets you're interested in, because obviously over the execution of a program, you're going to open all kinds of DLLs and maybe shared memory files or configuration files and so on. So you typically filter that and you say, I'm interested in this specific input. And then you map that through the file descriptor to later on the reads into memory. And then you basically, tainting is a term that's used to basically say that this is dirty memory. This range that was just read in through the system call is a memory that we don't trust because it came from an external resource, something that an attacker could control. I could send you a file, and when you read that data into memory, you shouldn't trust that data because I obviously could put anything in the file I want. So you start off with this one chunk of memory that comes from an external place, and then you need to track it as a tree-like propagation structure where at each instruction that accesses memory from that block would get copied into a hierarchy of dependencies, right? So let's say I copy in a file, I'm looking at the first 4 bytes with a magic number to make sure the format's correct. Well, that's going to be a series of assembly instructions. When you move that memory into a register, that register becomes tainted. If that register later gets moved into another part of memory to store part of that structure, you continue to propagate this on. So there's simple rules, taint propagation rules. Again, I talked about this extensively previously, so I won't go too much deeper into that. The whole idea is that you end up with this large tree of data dependencies. And once again, we need this so that in the end state of the program, which ideally in our case is an exception, we have this tree of data dependencies that then we can walk and use graph theory algorithms to learn what the transitions were that led to the actual execution point that caused the crash. And more importantly, in the constraint solving side of things, we know which instructions interacted with the data on the way there, and we can see what the comparisons were that then set the flags that then caused the control flow logic to change. So dynamic binary instrumentation, essentially if you're not familiar with the internals, I'm not going to go too deep, but that's like a JIT. Just think about it like a JIT compiler for x86. It takes in the raw binary code, disassembles it as well as it can, and allows you to inject, modify, and manipulate the binary at will, and then puts it into a code cache. And so all future references to the original binary are reflected into a code cache, and this is how you efficiently are able to interleave callbacks to your own analysis functions after pretty much every instruction. So in Taint analysis, we don't actually have to hook absolutely every instruction, but any instruction that causes any form of data flow. So that's, once again, moves from memory to registers, registers to memory, things that indirectly set flags, pushing to the stack, all this, and anything that essentially will propagate influence from this external data needs to be tracked. So it really does mean that about 80% of instructions need to have a callback injected just after them. So DBI is pretty much the way to go. Static binary writing might be a way in the future, but ultimately, Pin, Dynamo Rio, Valgrind, if you're willing to take the heavyweight hit in the single platform support. But most of the tools right now that are available are using Pin or Dynamo Rio. There's off-the-shelf solutions to this right now. We use the binary analysis platform from CMU that we've heavily modified for our own tooling, but you can go download right now BAP 0.8. It comes with a pin tool, it's ready to go, and it will output a taint trace with the protobuf format that you can then later on parse yourself for whatever purpose you like. There's also a library called libdft. It's a standalone library that just has the taint propagation logic in it. So if you wanted to use a different backend for the hooking and tracing, you can do that. And then just call into this library, statically compile it in for efficiency, but call into this library to maintain your taint analysis tree. It's slightly incomplete, but it's well designed, it's very efficient. It's pretty cool. So now we have code coverage, we have taint analysis, we have our engine that we're using to add our hooks to do efficient taint analysis. And the next thing we want to do is look at symbolic execution. And symbolic execution is a term that's used to basically say that we're going to emulate code using the formal logic engine, the SMT solver, a SAT solver. And in order to do this, we need to translate what the native ISA for your x86 ARM, whatever your target processor is, into a language that the SMT solver can understand. And there's a standard language called SMT-lib. And there's several solvers. There's Z3, there's the ICs, there's STP, there's several options, but really the most modern one that's available is Z3. And what we're trying to do is figure out what's the efficient way to transfer the algebraic logic that's expressed in the syntax of your programming language, whether it be assembly or a high-level language, into this format of SMT-lib. So here's a simple example. It's that same canonical example. If you were to encode this into SMT-lib, I did use a little shortcut here, but generally speaking, this is exactly what it would look like. You want to translate you've got a car buffer, so it's an array of integers. You have a function, you've got a variable named n. Basically what you're trying to do is when you assert, you're initializing values, then the logic in the next, the ITE, that's for if then else. It's just like the C code next to it. The decimal representation of the hex values of those ASCII characters are being used in this case. But basically this is just a simple one-to-one mapping. Now the goal of using an SMT solver is that you're able to ask it questions about the logic of the code. You're able to set an initialization point and then say that you wanted a certain type of endpoint to exist. And then you can ask it, what are the constraints over that logic? And what inputs do I need to modify, or what? If I don't if I don't assert all the input values, it will tell you what the input values would need to be to get to the end state that you're asking me about. So in this particular case, since we're incrementing n every time one of the byte matches correctly, which you probably wouldn't see in real code, but here, we're looking for n equals 4, meaning that all 4 bytes matched. And so that at the bottom there in the assert n equals 4, we ask it what would be required to get the n equals 4, and it will basically tell you that your input would need to be BAD exclamation mark. Now we can look at this and it's very obvious. So let's look at one that has ranges. Also very obvious if you know basic algebra, but here's one where we're going to say we want, at the very end there, we want ret to equal 1, right? That last assert is saying that our end goal, our end state goal is that we want ret to equal 1. What would x have to be, or give me a solution that would get n to equal 1. In this case, we can see in the code logic that if x is greater than or equal to 50, then we will achieve the goal that we want. So it's very clear to read in C code. But this, of course, expands to much, much, much larger blocks of code. In this case, of course, the solution that's given to us at the bottom is a model that describes that if, in fact, we give x equal 50, then we will return 1. So we'll revisit this in a demo a little bit later, but just to give you a brief overview of what symbolic execution kind of looks like, that's what we have. So the last part is the constraint generation. After we know, now we have an engine that can give us answers if we tell it a series of constraints, right? That's kind of the whole point of that little brief overview. So in pseudocode, block logic or control flow logic is simply a comparison of some value to another value, and then you take one branch or the other. It's a tree. And so we observe these constraints through our tracing, and then we record them and try to generate a formula that we can pass to a solver, and we can manipulate that formula so that we get different outputs. Okay. So if that pretty much the same logic is right here in assembler, it works all the same way. You have a comparison there at the +9, that will set a flag, and then there'll later on be a jump. In this case, it's the next instruction, but if you do, reverse engineering, you know that the jump doesn't always occur immediately afterwards. So when we're looking at our taint trace and the interaction with instructions, what we're looking for is the comparisons that occur along the way. And we're looking, because those are the things that are going to control, later on, control flow, right? Where we go in the program. So essentially this is just if x equals 1, then printf, else, bail out. That's pretty much what we're looking at here, pretty simple. So to explore alternate, so we hopefully, if you guys have all followed along here, we've figured out a way to go from x86 code to knowing that we need a representation that we can pass to a solver, and we can create, over the path of one execution, we can pretty much do that straightforward. The question is, how do we get to other paths, right? That's the whole goal. So the way that you do that is that you start to say, in these conditional constraints right here, in these asserts, when you are modeling a whole program, that's going to be, as many or more instructions than actual assembly that was touched by the data. So you're going to end up with hundreds and thousands of constraints there. For each one of those constraints, you can modify the condition to the solver. You can say that here's a model of exactly what executed. Now, if we want to go to a different code block, then all we have to do is change the comparison from a greater than to a less than, and the solver will output an answer that says, oh, sure, if you supplied this input, you would have gone to the alternate branch. So that's kind of the theory about how we apply this. And then if we do this iteratively over each single comparison, then in theory over a code graph, you'll be able to visit all blocks. If you were to map this manually, it would have looked something like this, right? Let's say we have that 4-byte comparison, we're looking for BAD exclamation mark. So we're going to seed the input the first time we run it with GOOD, just a good input. We're looking for the bad input, we're going to start with a good input. If you were to just draw this out in the true-false branch logic of how that occurs in the program, you'd end up with a tree like this, where on the far left side you have all false paths because none of the characters match what's being compared against. If you look at the next example, you can see that one of the branches took the true path because we're iterating through this. We're passing it to the solver. We're inverting that last branch of comparing it against the fourth character, and then the solver is saying, oh, well, if you solve this formula, you end up with GOO exclamation mark. It's going to give you the appropriate last solution because we inverted the last branch, right? And so you continue on and iterate through this, and you can just see basically that along the left side is the false path. If we step up a layer there, we take one true path, and then we take another false path, and so we end up with GODD. Only one letter has changed. If we take two true paths on the next one, then two letters change, and so on. So all the way to the right, if we follow the logic of this, each one of these branches would be an inversion of the formula. And here's kind of what it looks like if you were to write it out symbolically. Not in SMT-lib format, but in kind of formal logic. So we're going to take the second to right solution there, right? So we have 3 correct letters being supplied, 3 correct bytes. And then we're going to start off with that 4th byte being wrong. So we have BADD. This is after maybe 12 or 13 iterations of the solver, which right next is going to be a demo, so if it's starting to lose you, you'll see exactly what I'm talking about. But if you were to just kind of think this out manually as an exercise, like if it was in a textbook, you would start off with an input. In this case, it's 3 of the right characters, and it's just missing that last one. So the formula that we would end up with is input byte 0 was correct, and byte 1 was correct, and byte 2 was correct, but in byte 3 did not equal exclamation mark, which was the logic in the code. So we have did not equal. Well, for each one of those comparisons, we can generate a new formula. In this particular example, there's only 4 comparisons being made, so we only generate 4 new formulas. In the execution of a real program where you might have hundreds or thousands of comparisons being made, each iteration you can make a new formula, right? So in this one execution, although we can visually see that all we need to do is change one character, a system that's automatic would generate 4 new formulas that would try to get you to different paths. And so that's kind of what it would look like. So let's flip over real quick and see what this looks like in a real context of code. I'm going to have to modify my projector settings for a second. So we're going to talk about the architecture of how all this works in a minute, but I just want to kind of show you why this works and why this is important. So what we have as our tool here it's the complete re-implementation of the Microsoft Sage system, more or less. Complete in the basics. It's missing some optimizations, but it's a complete bucolic testing environment. Basically what you do is you feed a target program, a source input, and you can give it a format of how to use the input if it requires a series of arguments. And what will happen is it will generate some samples. So let's get rid of those real quick. And if we're lucky, it'll generate some crashes. Okay. So what we're going to do is we're going to run this test program. Which is that main function right here, which is the canonical example that we've been talking about. And we're going to give it the GOOD input, right? So we're going to go ahead and exercise exactly what I was just describing on the graph there. So we just run this. Yeah, it's not going to run C code. Never mind. Okay, here we go. So what we're doing is we're running the test application first under the pin tool that will take a code coverage trace, because we want to make sure that we create a mapping of all possible paths, and we want to make sure that each new path each new input will get us to a new path. And the next thing we do is we run that underneath of a taint trace, and the taint trace will give us the output of what that GOOD initial input, where it went in the program, and it will show the constraints that are in the code. And then it will create that symbolic logic representation of the code path that was executed, and then it will generate a series of new formulas that will reach the other paths, right? That's the whole theory here. So to see what happens is in the sample side, it looks about 15 different iterations to get through this entire program. The SOL files are actually the solutions that it came up with for exercising different paths. So the first one will be GOOD. The next one will be, BOOD for bad. The next one will, so this is walking that graph just like I showed you visually as it's going through flipping true or false branches, right? And then the BB files, those are the basic blocks that it does for coverage to make sure that the input is going to go somewhere else. So we have all these samples. Now, we hopefully achieved what we were looking for, which is that one of those samples would have been the BAD exclamation mark. So let's look in the crashes directory. Sure enough, let's see what the input is, as it should be BAD exclamation mark. And of course, if we run it with the targets, we get a crash, right? So very simple example, a canonical example. If you can't do this, then your code's not working. This is just a proof of concept that the code does in fact work. So hopefully you guys all followed along and see that this is a working concolic test environment. So we do have two real-world examples, so 0-day and Graphite 2 and LZ4 example that I'll be giving at the end of the talk. But so if you're just wondering why I'm rambling about these different things, this is why. This is what comes out of it. So we can do a here's all the different solutions that I try to find, which is just a complete exercise in the graph, right? So everybody follow that? That's a working concolic testing environment? Okay. So So I got turned on to this stuff. I mentioned where I'm at today, but before I started working with SourceFire and Cisco, I was at Microsoft for about 5 years. And Microsoft, in the time frame that I was there, was rolling out this technology for the first time in a production environment. They called their version Microsoft Sage. And this was an extension of the original work done by Patrice Godefroy on Dart. And then he worked with David Volnar, who was going to school at UC Berkeley, and on his PhD, and they published a paper called Automated White Box Fuzz Testing. And that pretty much describes the internal mechanisms that are required to make the concolic fuzzing work, and it contributed a further enhancement and optimization beyond the first 4 papers that were out there. So literally between 2005 and 2008, there was 5 papers released through just 3 original researchers, and since then in the hacking community, there's been some effort. I know here in France, the Sogeti researchers did a fuzz grind implementation, which was based upon Valgrind and implemented something like this, but it lacked robustness and it really wasn't very efficient because it was using Valgrind. And it used an earlier model of how to generate the new formulas that will get you to other parts of the code. So having the exposure that I did at Microsoft, I saw what it looks like when this really does scale. And they had maybe 100 machines, or maybe roughly around that, fuzzing during the 2007 to 2008 timeframe, which was in the Windows 7 release, like when they're testing their internal code, and Office 2010. So fortunately, I was there to see the motivation behind this. This came out of MSR, and then I was working in what's called the Secure Windows Initiative. It was in conjunction with like MSRC is the most external facing part of that, who would interface with you if you submit bugs. But there was a couple other teams behind that was doing the engineering and the actual reverse engineering and crash triage and things along those lines, fuzzing and finding new bugs. And so I was fortunate enough to just happen along and read this paper and realize this was a resource in Microsoft that I could use, and then we brought it to our security testing and kind of applied it for all kinds of other products. So the way that they did it, Microsoft has like the real benefit of having MSR. They're one of the few companies still around that has a real researching department. And unfortunately, just recently in the last year or so, they've downsized that. I don't know if you guys follow that sort of thing, but they downsized one of their areas in California, but they do still have a large MSR department, which means that they have some really, really great platforms for binary engineering. They actually have what they call the binary engineering group. And they use this for everything from applying DRM or post-compilation hacking and reordering of binaries to writing tools like this. So when we break it down into the things that we need to do the concolic testing, like I was saying, we need a debugger, obviously, because we're looking for crashes in this context. So they have App Verifier. That's actually something available to everybody. It's a tool that you can download from Microsoft. They also use a DBI framework called iDNA. And I would say that iDNA, the trace recording is closest to the recent system that was released called Panda. Panda, to me, is evolutionarily tied to BitBlaze in the concept. It's a QEMU modification, and it uses LLVM for its intermediate representation, and it has a very lightweight temporal trace recording, so you're not recording multi-gigabyte traces. Similar to that, iDNA doesn't record multi-gigabyte traces, it records temporal data, and then when you re-execute the program, it hooks it and injects just in the inputs and outputs and timing data, random seeds, things like that. And then they have a system called Nirvana, which allows them to re-execute these traces and then apply analysis to them. So that's how you would do your coverage analysis, taint analysis. And then they have their own, the symbolic executor is always going to be a custom piece of code. It's how you tie together your platform and translate from your x86 to an intermediate representation. So like we use BAP because we get that for free, right? So the pin tool from BAP will output this protobuf format that's not using an IL, but you can lift that into this engine that's basically a rewrite of Vine, which is what BitBlaze used to use. But it's an engine for doing reasoning about program analysis. It does all kinds of graph recovery algorithms, and they've written a complete type recovery system over a decompiler, things like that. It's a very robust IR. If you're familiar with REIL from Halvar and crew, or maybe I think Rolf was probably part of that as well. If you're familiar with that as kind of one of the types of IRs that's been talked about in the hacking scene specifically, this is another IR that's been utilized in program analysis frameworks in a larger context, really. So in any case, most people, if they're going to do symbolic execution, will translate from x86 or whatever the target architecture is to an IL, because the IL expands your target architecture into the micro-operations, right? So anything that is indirectly influenced by an x86 instruction, like your flags or your stack pointer or whatever it might be, this is explicitly expressed in the IR. And it's a reduced instruction set, so it's a RISC-like maybe 30 instructions instead of whatever we're at now, 200-300 instructions in x86. So when you write the rules to translate from this reduced instruction set to SMT, there's only a much smaller amount of work that needs to be done. And also you can write one backend that converts from their IL to SMT, and then you only need specific front ends from going from ARM to IL, or x86 to IL, or x64 to IL. So in any case, Microsoft had that using TrueScan, and then finally Microsoft had this efficient SMT solver internally that they used called Z3, which is now all public for us as well. It came out of MSR, the Rise for Fun website you might be familiar with. Rise is actually one of the groups inside of MSR. So optimizations, I just pretty much will direct you to the paper to read heavily on their optimizations, but when you convert from x86 to the IL, you're expanding the amount of individual instructions that you're going to end up translating to SMT. And SMT solving is very slow, like I was saying, like way slower than doing software emulation, right? When you do software emulation, you're interpreting each instruction and you're writing to a piece of memory that represents either a register or the memory of this process that you're virtualizing. Well, in the case of SMT, you are not constricted to concrete values or explicit values, so you're actually reasoning about ranges of values. And so it's much, much slower. So the optimization layer is critical for doing large-scale application of this type of approach. And I'll talk about where we're at and all that and our limitations. But generally, they had two major things that brought the concolic testing up to the next level where they could apply it across the company. And that was, first of all, they figured out that, I mean, it's kind of an intuitive thing when you think about it, but the first research was only negating the constraints from like this symbolic representation of your code path. They were doing a breadth first search or a depth first search, right? They were just looking for, how do I get to that next block? Rather than realizing that, well, if you have one formula that represents a whole path, you can generate the same number of formulas for each branch that's in there. And then that's why you do the code coverage pass to filter out the ones that will all end up in that bucket. That's just, you didn't have a complete format or something like that. But so you become much more efficient by only having to trace one time and then generating multiple formulas later, and then solving to see if those formulas generate new outputs. So, because taint tracing is really expensive. And then the other one is they do like structural recognition or structural analysis of the program. So they identify loops, which obviously if you're iterating through a loop and you're doing a linear recording over time, you're going to have multiple instances of that loop in your trace. So when you convert that, if you just do a direct one-to-one translation, you're going to be translating many, many more instructions to the solver's language than necessary. So by doing structural analysis first, you can eliminate a lot of superfluous analysis that you'd be pushing off to the solver. So that's really the big need in what we're doing right now. That would be one of the biggest efficiency gains possible on the hard science side of things. There's also the whole like pin is slow to initialize, and I'll get more to that. But if you're interested in this stuff, like if you're actually in academia right now, you're doing research on, maybe you're going to postgrad studies or something, and this is an area you're interested in, there's a lot of room for work in the optimization layers of doing this type of stuff. So I would just point you at the paper. There's plenty of really heady, hardcore analysis to be done there. And so basically by doing all that, having the benefit of having MSR and having all these people doing that type of research, Microsoft was able to make a scalable system. Found a third of all the bugs in Microsoft Office in the 2007-2009 timeframe. And also a good number in Windows as well. But that was, you have to remember, this is like the time of integer overflows were still everywhere, and the formats were just horrible. They were architecting Microsoft Office so that it would have like a parsing layer that was more or less what I think they called it the Guardian or something. But they were looking for ways to sandbox their parsing engine just itself because there were so many parsing errors. And so by applying this to that type of target-rich environment, it was very successful. The lessons that they learned by taking the generational approach was that the vulnerabilities discovered are at somewhat shallow code depths. And this means that essentially by only going through a series of generations where every generation allows you to reach pretty much, like if you have one path through the code, you're generating a new formula that ideally will get to every possible inverted branch, right? So if you take true, true, false, true, that will generate one that will take the alternate branch each time. So you only need to actually run through this a very short number of times comparatively to what it would be for fuzzing iterations if you're doing mutation fuzzing or doing the traditional depth first or breadth first search. So a lot of the vulnerabilities were discovered at shallow code depths once you get to the logic that you're interested in. Symbolic execution state is going to be limited because we're talking about ranges of values, and so the way that it's represented internally is pretty expensive. So just pretty obvious stuff. You want to wrap things at the lowest level possible without having much logic in between the business logic and the parser that you're going for. And you can look in their paper, but they have, of course, seems to be the required graph that shows performance over time. And pretty much the small number of generations due to the way that they create the new formulas and do the solving requires just a few iterations. So our version, MoFlow, internally we call it eGAS, which is just Sage backwards. So when you see me typing into the console, that's what you'll see. Later on we'll rebrand it or something, but it's open source already. So if you go download the BAP tools, the MoFlow BAP tools, you'll see it called MoFlow eGAS. But this is our version. We modified BAP pin tool so that when it crashes, we can collect memory dumps and reference when we do the taint analysis overlays what was where. Added coverage information, which surprisingly is just not a part of the BAP framework to begin with. For some of our triage stuff, we mapped the file descriptors back to the input file names so that when you're using it interactively, it's in a more usable state. Modified some of the robustness on the Win32 side. Added our own debugger to it, so on. We wrote a completely custom symbolic emulator or executor inside of BAP, so they had the ability to do some offloading of solving already in BAP, but we have a completely new core, and it actually modified some of the BAP cores, so it's an official fork as opposed to just a patch to the BAP firmware. We use Z3. Originally we used STP, but Z3 is just more performant. And then, of course, like the eGAS tool ties together all the pin execution, the running of code coverage, running the taint analysis, pushing it off to the symbolic executor, and so on. So that's what you saw when I ran that quick example. We'll run another example here in a second. Limitations, the taint tracer from VAP is not as optimized as it could be. The pin tool itself actually has a pretty long initialization, so we're kind of working right now on a way to snapshot post initialization of pin. So if you have a large application where you're hooking like every single instruction, that takes a while to parse the file and add all your hooks and then put it in the code cache. Well, VAP has an API where you say go init and then it does all this and then it returns to the start of your initial target. So without having to deal with any of the nitty-gritty of remapping file descriptors and some of the complicated things when you're doing network traffic and stuff, there is definitely a shortcut to getting the initialization for pin. So that's one of the things we don't have yet, but it's a short-term project that will be an open source tool that we'll release as well. You can apply it in other contexts. Pin also is limited in the sense that you can't flush the basic block individually. So if you want to remove hooks because you're not interested in a path, or if you want to, if you're in the code coverage context in particular, you're just looking for a hit trace because you're curious about where you went and you don't want to hit your hook every time you iterate through a loop 1,000 times to copy bytes, you can't do that in pin. You can do it in Dynamo Rio, but not in pin. There is going to inherently be a trade-off between the amount of input that you can track and the depth of code that you can emulate through the symbolic execution, because you are declaring each byte of your input in the symbolic emulator, right? So when you initialize all these asserts, you're generating large values in the SMT solver, and then all those have to be reasoned about when you're tracing, hundreds of thousands, if not or more, instructions. And so there's a trade-off for code complexity and depth and the input size that you can watch traverse through it. Once again, we don't have the optimizations that Sage has, so essentially the conversion from the VIL to SMT-lib it's just not efficient. It's not aware of the structural constraint, or the structural layout of the program to minimize the amount of work we push out to the solver. And but it does work, so that's the good news. I mean, obviously you saw it works in the simple case, but this actually was a bug that we originally found. Oh, you know what? I was totally going to kick this off beforehand. I have the files from it. So this takes like, when my hard drive isn't full and fragmented, it takes about the time that it takes me to get this far in the talk, about 40 minutes or so to find the first trigger for this bug. But basically, Graphite 2 comes with a program. It's called Compare Render. It's a built-in test tool that exercises a lot of the code for you. And it comes with a test TTF, tiny TTF. And we run this under MoFlow for about half an hour to an hour, and it finds this bug. So let's flip over and just look at what that looks like in a debugger. I apologize, I meant to kick this off at the beginning and see if we could have finished it in time. You can definitely download this, it's included in the package. You can replicate this. This is no bullshit, real bugs. So let's get over to oh, you're not seeing this right yet. Okay, that's fine then. So the outputs that you get when you run through the whole system, including our Taint tools, are things like this. So we have the Graphite, the original input that causes the crash, the Graphite crash TTF. That was a crash that was generated in the crash file, and I just stored it for reproduction purposes. But you can see that the crashes directory created several iterations of the same type of crash. In the samples, you can see that we generated about 5,000 almost. We had to generate 5,000 different conditional traversals to get to this parsing bug. So that's why it takes about an hour or so to get here. The bug itself, if we launch Graphite, Is that font too small? It's not too bad, is it? So, well, I have this documented on the slide right here. So, okay. So basically, what we're seeing is that the tiny TTF took about 8,000 iterations of manipulating the inputs such that it could traverse the test file, which is using, of course, the Graphite 2 library that it's linked to. What happens is essentially we crash in this location right here, which is a F-read with a gigantic size. There's a data structure inside of the true type font that's a table of pointers to other sections, and obviously you can see in this case that the get table function is what is reading that code here. Yeah, here we go. So the F-read you see down at the bottom there is the issue. That's because the malloc fails above that, because the table length size, which came from the get table info API, like we see here, was overly large, right? And so it adds it to an offset, tries to allocate a super large chunk of memory, fails, returns a null pointer, doesn't check for that, and then we end up reading into a read access violation. So this is a real world bug. It's actually 0 day. I mean, it's only a read AV, so we haven't been too quick about reporting it. I've been talking about it since June. But you know, it just kind of shows the magic of this kind of thing. We just let it run for a couple hours. You give it a well-formed input that just came with the test platform, and just by observing the code, looking at the constraints, generating new formulas to represent other code paths, it just finds bugs for you. And it's a much more elegant solution. It doesn't apply at the biggest scale, but it's a precise traversal of the code graph. You're not guessing when you output new inputs, right? So that's part of the magic. Between that one and the first one, those were the real-time demos that I had. The one last note I'll make, this is pretty much the last couple slides I have, is that not only can you use this to find new bugs, you know, if you have an idea about a certain format or something, you can also use it to quickly create repros for bugs that you know exist, right? So an old friend of mine, Don Bailey, back June 26th around recon time, had found a bug in LZO, LZ4 compression, right? And there's a particular type of flag in the LZ4 header that has a structure called the literal run. And it's funny because people probably don't even realize this exists there, but what it says is don't actually compress this next series of bytes. So I want a compressed file, but don't compress it. So the logic there, even at a design level, is curious. But in any case, he did a source code analysis of this and found that he was able to trigger a bug that was an integer overflow that led to actually a writable write AV, right? And so in particular, he and I were working on this a little bit together after he found it initially, and we had taken the standard LZ4 package and then wrapped it in a function that utilizes it the way that the Linux kernel uses it, which doesn't do the proper validation like a header validation. It actually expects to receive a byte stream that's already in LZ4 compressed format. So if you run it from the command line tool, the user space tool, it'll do validation and fall over and like exit out cleanly. But on the Linux side, what we see is that the null bytes in this literal run structure are interpreted as 255. So there's an accumulator variable essentially called t in this code snippet on line 59 here. That every time the unlikely event that the byte that it's going to observe is 0, it adds 255 to t. And t is a 32-bit unsigned value. So you can do this as many times as you want. You control the contents, obviously, of your LZ4 compressed file or LZ4 compressed buffer. And so essentially what that means is you have arbitrary control over the value of t. It's later on used in a obvious integer overflow at first glance, where at this point we're basically copying from one buffer to another. T is synchronized. The Linux kernel in particular adds this little bit of code where it adds 15 to it. So you can cause it to wrap so that it only copies basically the first 16 bytes of your buffer, and then returns out of this loop here, that while loop, while still having a very, very large value set, right? Because it was adding 15 to it in the comparison, so it was saying, you know, as long as it's in a certain low range, then we'll go ahead and loop until it's done. But at the exit of this loop, it's actually set to a very, very high value, a near FFFF, right? And so essentially, IP and OP values at the very end there will be set to this pointer out into the high memory space. And when we run this under EDAS, what we did is we took a well-formed LZ4 input. We ran it for, I don't have my notes up anymore, but this is about 6 hours, 22,694 seconds. And it generated a crash, and just one crash. And basically that crash was, in fact, in the LZ4 uncompressed function. We can see that it's reading and referencing the IP value there on line 125. And if we look at the local variables, we could see that, in fact, we did point the OP and IP like data variables to this like high memory space. So this was just literally a matter of saying, oh, this guy found a bug. Okay, let's throw Sage against it. Give it a simple input, let it run for 6 hours, and then boom, you now have a repro for that file. So, I mean, it truly is zero effort, like nothing more than just giving it a one well-formed instance and letting it do all the magic for you. So that's what I'll leave you with. The binary differencing part, like I said, is just too long. So we're going to close with this. Hopefully, you see the value of concolic testing. You see that this is almost a magical bone-finding tool within the constraints of the performance and everything. So it's open source. It's available for you. I hope you enjoyed the demos, and thanks for your time. I guess just one last point I'll make. I apologize that I didn't get to the BinDiff stuff, but I do have Ryan Pentney and Martha Noga here from my team. They were doing a lot of the BinDiff work, and Piotr Bania was doing a lot of, Paul Janik was doing a lot of the work on the Sage side of stuff with me, so I don't want to end without at least recognizing their efforts as well. So the code's released. Here's the URL. You can find me on Twitter or out in the hallway having a beer if you have any questions. So thanks. Or do we have time for questions?
Yeah.
Yes.
Any question? Wow. So you probably know that Sage and probably your system are blocked by checksums and slowed down by compression code. Whenever you have compressed data and data with checksums, because they can't reverse the checksum. So
well, actually that depends. The checksum is reversible. Some forward hashing wouldn't be.
Yeah.
So if you do a CRC,
like an MD5, for example.
It can solve a CRC.
Yeah, but MD5 would be hard. I'm wondering whether you plan on putting like an initial layer of basically binary modification where you detect the checksum in code and basically nurture it and maybe pass through compression code.
So sure, and you would do that by looking for magic numbers that are typically used in hashing or forward one-way hashes, essentially. So people that are familiar with crypto or are not familiar with crypto, essentially the way that you can identify a crypto function is through looking for specific initialization values that tend to be utilized in the implementations that are available, which are almost always reutilized. So yeah, that's possible. I don't have a framework yet, or I don't know of one that's out there. It would be a generically useful tool, no matter what type of fuzzing you're doing. But the answer to that is we don't, of course, as you know, have a solution to hash functions. But CRC32 functions are solvable through something like this. It's really not a one-way function. But if you had to have a specific MD5 sum or like a certificate value or something in a header of a signed binary, of course, this is not the appropriate system for that without hard coding it.
So in your Taint tracker, how do you deal with Taint explosion when using, for example, a tainted index into an array?
So, okay, that's actually a flag that you can choose whether or not to use array indexing as a taint propagation. There's not a concrete answer to how to solve that. There's research right now coming out of the Berkeley that's doing some work on furthering the taint propagation rules. So there's several things that you run into. Array indexing is, the question is basically, if you have a pointer into an array, you control which index into that array that you want to, that you're going to reference, right? And the question is, do you taint the entire array knowing that if you have control to it, generally speaking, you could technically use any of those bytes to read into there. So that's a trade-off in some small instances where the array isn't large, you could turn that on. We've run into some of those issues in parsing specific media file types, and when you get to the triage tool layers that I released last year, you sometimes can lose the ability to do a back taint trace if you don't propagate enough taint. Another instance of that is like when there's a constant assignment. So like if you're inside of a function body, or inside of a basic block or something, and they assign a static value to a variable that you have tainted. Well, if you control the control flow that gets you into that basic block, technically you have a slight degree of control over what that variable is as well. So it's an active area of research. There's not a lot of progress being made there, but it's almost all done initially for a first static pass of the binary, and then informing the taint engine when you do your runtime taint propagation.
Have you tried it on other Sourcefire products? I'm
sorry, where are we at?
Yeah.
Okay. So actually, just now we're rolling it out in the Ironport product line, and we were rolling it out to Claim AV until I was going to give you guys a nice demo of a bug we just patched this week. But it's interesting. The architecture of Claim AV writes to a buffer file. Like, let's say you open a file that has sections in it, or it's packed or something. It writes it out to a temporary file. And that file is modified in transit, essentially in the same execution. They don't close the file descriptor to reopen it. So architecturally, we need to work around and make a special case for something like that. Essentially, if you write to a file that you've read tainted data in, you've desynchronized the context in your taint tracking. So the long and the short answer is that yes, we're starting to ramp that up over the next 6 months. Specifically, now that Cisco has a larger portfolio, we haven't applied it to Snort. Claim AV was going to be our first target, and we're using our other fuzzing platforms for that because it's not compatible with taint analysis.
So I think it's finished. We're going to Taint. So thank you.
All right, great. Thanks, guys.